So for the next hour, we have one last set of presentations from the SEGS lab. And if you remember the approaches that we were taking, the approach that we take to systems is we have the operational level, we have the tactical level, and then we have the strategic level. And it's at that strategic level that the system pulls itself together, and you begin to see the sum of the different parts making up more, well, the whole making up more than the sum of its own parts, so that there's emergent properties that occur at a larger scale. And the way that we do this in the modeling world is by using, in our particular case, there are a number of different tools, but ours preferred mode is agent-based modeling, where you have individual objects, and in this case it could be pigs and people and facilities and what have you, that have some interaction, and out of that interaction emerges some collective quality or whole results. And to do that, we have these computer simulation models that the next round of folks are going to talk about. And I think it's Gabriela and Eric, and is Ollin, are you speaking as well? Okay, so our speakers for this block will be, you've heard from Eric Clark and Ollin, and the new person, the new face you'll see, although she's asked a few great questions, is Gabriela Bucini. And Gabriela is a postdoc in our lab and at the University of Vermont in the plant and soil science program. And Gabriela is also an ecologist and is incredibly deft at communicating these ideas, so much better than I. So I'll bring up Gabriela to give you the presentation on our strategic level modeling. Gabriela.
All right, so welcome everybody. It's so nice to be here. This is really a great opportunity. Thank you, Julie, for organizing this. It's beautiful to share ideas. And so we're going to be three of us, okay? And we start to go to the peak of the pyramid and start thinking strategically. So here we're going to use the simulations and strategically see how human behavior, oh, thank you, this is awesome, human behavior control disease in a production system. So Eric and Ollin will present with me. And we are all part of the University of Vermont, SEGS Lab, and ADBCAP project. So here we are at the top of the pyramid all together. And what we want to recognize at this level is that farms are not isolated entities. And in the whole production system, there are other stakeholders. And what happens at the farm level, that culture of biosecurity and disease aptitude has repercussion, it ripples throughout the system. So that culture doesn't stay isolated in the farm. So to tackle this issue, we need to simulate a whole production system and see how the disease can percolate through the system given the culture, the biosecurity culture in the system. Another important aspect is to recognize that these three levels, I think this is the one. Okay, these three levels are not independent. So what happens at the operational level, at the tactical level, really emerges at the strategic level. And then in the other direction, when we think strategically, so we plan and we think about policies on biosecurity, they will influence the investment in biosecurity, and those investments will also influence the kind of biosecurity that farmers and workers need to implement on the farm. So remember this interaction. And then let's go back to our initial question. So epidemiologists have done a great job, and they inform us on how virus can spread. And our contribution to understanding disease spread is to add the human behavioral side in the issue. And the question then becomes at the strategic level is, how does human behavior affect disease, and we'll see also market dynamics in a production system. Okay, takeaway. So the key words for this presentation is variability, or if you want, unpredictability. So in this graph, I'm going to convey the message. We have results from some simulations. And on the horizontal axis, we have time. And here we count disease incidents. And in this case, we started an outbreak in June 2014, and we see what happens to incidents. When we look, well, we have different scenarios. Let's look at the red shades here. And this is a scenario where we had high risk tolerance in the system. What happens after the outbreak? Very hard to decide. So the variability of what can happen afterwards is humongous. It can become a pandemic. So the oscillations are due to the fact that this virus is seasonal. But still, the variability, it can become a pandemic, or if we're lucky enough, the disease can die off. But very hard to predict what can happen. As we move to more risk-averse cultures within the system, look at what happens. Here we look at blue shades. We can really control what happens after an outbreak and have a better handle, better management of consequences. So look at the difference and remember variability and unpredictability. Okay, I want to give you immediately a flavor of what is an agent-based model. I think it's important to see. Many things happen in here, but let's focus on the left side. Okay, oh, this is, can you wait a second before starting? Okay, you had it. Okay, can you guess what happened there? Just you saw the outbreak right there, right away. This is just for demonstration. We only have a system with 800 farms for this demonstration, but we ran the model at the North Carolina level, so state level. So here, each circle on the left is a production facility. Different colors is because there are different types of farms. Some farmers follow the pigs from birth to finish. Some instead are more specialized and take only stages, so only piglets or only youngster or just the finishing stage. And this is important to keep in mind because of what, well, we'll see it later. And then part of the system, well, feed mills are going to become part of the systems. Sometimes auction houses, and these are the white guys here. Feed mills are the silos up here. And then we have slaughter plants. Okay, so all this will be connected in networks because there is transfer of pigs from one farm to another. Especially so when the when pigs reach the end of a stage, they can be moved. They need to be moved to the specialized facility. So we need to build those networks, also networks between feed mills and producers, and then the slaughter plant networks. Let's look at the right side. We need all these explanations so you can really enjoy the simulation here. We can track the number of infected farms in this first graph. Red line will appear. And then we can track the number of pigs that will be infected throughout the system. On this graph, also there will be a red line there. And then this is the part that is really important for us. We start with very low biosecurity, so very risk-tolerant culture in the system. And then we can see what happens when we move up towards more risk-averse cultures. I think we can start. At this point, let's do it. So we'll start an outbreak. You see, we'll have some agents here. And then we can track it. So look now also at the number of farms is increasing that are infected. This is really a pandemic, actually. We can intervene and then we'll increase biosecurity in some of these agents. So that's one possibility, just target some key agents here. Or what happens if instead we change overall the culture in the system and we move everybody towards more risk-averse positions? And then so we increase to medium. And we can see how this, the kind of effect this has. So we start to have a decrease in the number of infected farms. And we're lucky because at this time, we were able to get rid of the disease altogether. Okay? Questions? Was this fun enough? Yes? Okay, cool. What I want to point out here, so these agent-based models are really special. Their strength really lies in the fact that it's a bottom-up approach. So you don't model the outcome, you don't model the disease spread, but you model the mechanisms, the core mechanism that make the system work, and the core mechanism that control the epidemiology in the system. And then you launch the model, and you see what emerges. So it's the disease spread is really the outcome, and you can see what emerges from the mechanisms that you built in. Okay, we move. All right, so we had several really big milestones in let's say, development of the ABM. We call agent-based models. That's ABM. If you want to jump in at any point, just and so we'll see the main results that we had during the development. So a few things before we got into the results. I want you to have really the special features of these ABMs that will help you understand the results. It's for this model is for a swine production system with transportation networks. We transport hogs and feed. And then the virus that we're simulating is the porcine epidemic diarrhea virus that is transmitted either directly or indirectly, for example, with transportation trucks that are infected or the feed that can be also infected. And then this is the key. We need to build in the human behavior. How does human behavior come into the picture is by linking it to the level of biosecurity that each agent has in the model. We'll see more questions. Lucas, I see you very thoughtful. Is it okay? Can I move? If you have questions, please. All right, so.
Quick clarification, real quickly. We heard all morning about the fact that different human beings have different risk tolerances and different behaviors because of that. Are your agents variable, or are you, at least right now, setting a set risk tolerance?
They're variable. You'll see that. They are. Yeah, Eric will tell you about that. So we want to first visualize disease spread. We saw that. It happened. And then understand how the human behavior with different risk attitudes affects transmission of disease. And then we want to play with what-if scenarios. So that ties back to the first graph that we saw. What if we have a very risk-averse culture within our system? What if instead it's very risk-tolerant? What do we get? All right. You saw already our agents are producers, slaughter plants, feed mills. They have behaviors, so they grow and they exchange pigs. These are the producers. Slaughter plant will receive finished pigs, and feed mills, they deliver feed. And then this is the network, and it's important to see it because it's really on these networks that the virus moves. So we have farm-to-farm for hog movement, feed mills, networks, and then slaughter plants. This is what happens when you put everything together. And these are really the highway for disease spread. And so this is where also epidemiologists have helped us a lot building the model, because so the infection probability is from their work. So we learned that there are two things, that one thing that in particular that is important is the type of interactions between agents will affect the infection probability. So if I interact with a slaughter plant, I have higher risk to be infected than if I interact with another producer that is in my system. On the other hand, like what we add now is the behavior. So that infection probability also depends on the biosecurity of the two agents that are interacting. Okay, let's see more about that. This is where the risk attitude comes in. The risk attitude of the agent determines the biosecurity level of that agent, and that determines the probability of disease transmission. And this morning, Lyndon, this is for you. Right away, we saw that there is a range of risk attitudes. This is the beautiful graph from Eric. And then that is mirroring the level of biosecurity adopted, or the willingness actually to invest in biosecurity and the compliance at the farm level. So again, here you see here how we build the 3 layers of decision making into this model. Okay, let's see the milestones here. What do we learn from studying all these interactions, the networks? Just looking at that, there is a lot to learn. This is the work from Serge Wiltshire. And what he did, it took something that is happening actually in the hog production. Right? Steve helped me with that. It used to be very low specialized, right? Farmers would follow the pigs from birth to slaughter. But it has evolved a lot, and now there is higher specialization, and more farmers move to become very specialized and only take one stage of the growth. So he studied the disease spread and the percolation of disease in the network in these 3 different type of networks. Very low specialization, so very simple network. Very high specialization, it becomes much more complex. How does disease spread in this? So this graph really is a great summary of this. We take the number of producers and we see what is the proportion of them that got infected during the simulation. In very low specialization, green line here, you can see that the proportion of infected farms is much, much lower, significantly lower than the number of infected farmers when you have very high specialization. So the fact that you increase the contact point, the number of contact points or the nodes in the network makes the system way more vulnerable to disease. And then the other important finding from Serge is that slaughter plants and feed mills can be really hubs. Or if you want to think about maybe super spreaders, there is another fancy word for this idea of hubs and like weak points in the network. And then, okay.
If you have a question, I'll wait to hear.
Okay, sounds awesome. So we come to the first reflection at this point. So on one hand, specialization, correct me if I'm wrong, Steve, helped producers to become more efficient and probably lowering the cost of production, but also it made the system more vulnerable to disease. So when we think strategically about biosecurity and policies, how do we need to design biosecurity policies to account for these features, for this structure? Think about, these are all reflection points. All right, let's go to behavior. So in this version of the ABM, we applied what we learned from games and what happens when we provide information to agents. So they become reactive. They receive information from vets. Now we have vet agents. You're going to like this, Steve. And their risk attitude stays the same, but they can change the biosecurity while there is an outbreak during the simulation. Okay, let's see what happens here. So we human beings, okay? When there is a big scare, like swine fever now, we are all ready to increase biosecurity. With time, biosecurity goes up, either by investments or high compliance. But we're also human beings, and when everything is calm, nothing happens, we start to like relax a little bit, and biosecurity comes down. So these two opposite forces are in our model. Okay, I think it's time for Eric.
Thank you, Gabriela. So I'm going to talk and bring back the gaming simulations that we were discussing this morning. We've talked about integrating this human behavioral strategies into our agent-based model. Let's go back through and remind you of this biosecurity investment, or also known as the protocol adoption digital field experiment. So here we have each round starting with a single infection, and then an agent, so the human, gets to see across the board all this information and choose whether or not they want to increase biosecurity over time. So if we blow this up a little bit, you could really actually consider this as a bare bones version of that agent-based model. So we really try to get a lot of mileage out of these gaming simulations, as they are non-trivial to construct, deploy, get people to actually play these games. So when we built this model, we had a couple of ideas. We wanted to understand, how does risk communication affect the decision-making process? How does uncertainty affect the decision-making of each of these participants? As well as, how can we parameterize a simple version of the agent-based model and take this human behavior and then integrate it into the epidemiology? So to remind you, we went back through and we collected 1,000 participants from Amazon Mechanical Turk. This is how we developed our behavioral distributions. Hopefully not any of these puppies were in there. My Labrador might join the workforce if he keeps stealing the cat food. I'll have to put him to work. So what we did was we were trying to quantify this risk aversion spectrum through this biosecurity adoption game. We wanted to place or find a distribution of the behaviors corresponding to people who are trying to minimize their risk through biosecurity investment versus the gamblers. And what we found were these three big classes of behavior: the risk averse, who tend to adopt more biosecurity; the risk tolerant, who adopt very little biosecurity in hopes of achieving a higher payout; and then these opportunists, who change their behavior with respect to risk communication. So now if we look at these numbers, we can actually consider this as some sort of distribution of behaviors that we can now use to parameterize our agent-based model. And the goal of our research moving forward is to understand how will differing distributions, so quantities of each of these risk categories, affect the outcomes economically and the incidence of infections across our ABM. And recall that we actually validated some of these findings by going to the World Pork Expo and compared to a convenient sample of 50 actual stakeholders in the field, and found that these behavioral distributions seem to make sense for modeling this behavior. So using these gaming simulations, we've shown that we can identify these underlying risk behaviors and then create tools to recruit people, a widespread audience, and identify potential variability in their behaviors, and then implement that in our agent-based model. And I'll let Gabriela tell you how she did that.
A magic. Sorry, let's look at this. So that's what I did. So I took the population of our agents and I distributed them across all these risk groups. And then actually I took some extremes. So then I moved some of these producers across the groups. And then I started from, wow, that went. Okay, I built two very opposite scenarios where everybody became very risk tolerant and everybody became very risk averse. So those are a bit realistic, but they're helpful to understand, to give us a frame to discuss here. So if everybody in the system is risk tolerant. We are here, like very red. And remember the keywords, like unpredictability, very high variability in what can happen after an outbreak. So incidence can be very high. In general, it's like higher than when we start to move and become averse. If we're lucky, nothing happens. But as we increase the culture towards more risk-averse positions, really we can decrease the variability and have way more control on what happens after an outbreak. And then if we go back to the first graph that represent the time, the incidence through time, I want to show you this green line. So this is actually the observed incidents that USDA collected. So these are real records. And you have to remember, a PDV came to US in 2013. The data started to be collected in 2014. So that's when we also started our outbreak in the model. So in the beginning, in 2014, really it looked like a pandemic. But then look at what the swine industry was able to do in 4 years. And then, so it went from something that could look like a pandemic, and they were able to almost to increase control and reduce incidence to a case where it's similar to what we would get with very high proportion of farmers being risk averse. And then if we stretch a little bit the line here to 2018, we see, this is like a press release from the awardee here, only for us. Stretch out on 2018, we would see this halved, right? Incidence still. And the hypothesis here could be that because of swine, the scare, right, of swine fever, everybody has very, very high biosecurity. And indirectly is helping also PEDV to be under control. So remember that this is like a super cool findings. And so do you want to add something, Steve, on this? No? But yeah, remember this indirect effect. So biosecurity is not only tailored to one this virus, but it can really help overall protecting a farm and a system. Okay, I want to show you very briefly what happens when we look at the economics on the same type of scenarios. Okay, so first let's look at what happens for prices. Okay, we built in a supply-demand market in the model, and then we kept the demand for pork the same, and that meant that when there was less supply because of disease, the prices went up. And that was the case in 2014, where some producers really made a lot of money because of the high prices. So let's see if we can reproduce that kind of pattern in our model. So here we have, when we have 100% risk averse, and we look at the price, so the baseline price for a pig started like $160, $165. That was pre-outbreak in the model. And then when in risk averse, the maximum it reached during the outbreak was $180, $90. But with high risk tolerance, the prices went up really a lot. Like, I don't know what is the real price, whether this matches, but we got up to $210, $220 per pig in the simulations. So again, we see high variability of what can happen in an outbreak with some, how many farmers actually? Let's look. How many farmers did benefit from this high value? And Eric, you wanted to say something about this?
Sure, actually. So from this distribution, so here we see on these red markers, these are when we have 100% risk tolerant populations. And here on this y-axis, this is the percent of producers with a positive budget. So you could think of these as the winners, right? Up here, this means the system, over 90% went positive throughout some outbreak. And the
positive in budget.
Positive in budget, not in disease, right? So when we look back and look at this, the entrepreneur in me says, "Oh, look, during this 100% risk tolerant, look at these prices out here. There's a lot of opportunity potentially, and this really isn't the case. So if we go back here, all right, these are the points in which this is happening. Now look at this point right here. This is saying 40% of all the producers went negative that year. So that's a little bit, if you're thinking if this is your livelihood, are you going to bet that on about a little better than a coin flip? Right? So that is a dramatic difference.
These are for individual scenarios.
Yes, each point is a scenario. It's a scenario, it's a run. It's a simulation.
Right.
Yeah, so this is the overall output from...
It's not an individual
Yes.
facility.
Your domain took the industry, the 100% risk averse did not receive as high a price, but they were lower probability of losing money.
Exactly.
Yeah, so they didn't make much money because the prices stayed pretty stable because you can control the disease very quickly, and so you don't have those oscillations in price. And so many of them can stay in business. But once you are in the game of who knows what is going to happen, some become very lucky, and some, like 40%, turned out to go negative by the end of the simulations. And this,
we could see how clustered these two groups are. Whereas when you have all this unpredictability in the system, there's a lot of potential for a lot of losers, right?
So I want to reflect on this because on one end, 2014, for example, represented this, where it was probably one of the best years for the swine market. But then some farmers really lost big time. So the reflection for me is if we want to create a system that is somehow resilient to disease, what kind of biosecurity do we want to design so that there is a good livelihood for the farmers, but at the same time, how do you design biosecurity to give also the farmers the ability to make it? And another reflection that I have is that I wonder whether the farmers who really did well were also the ones who then had the means and the money to be able to invest more in biosecurity in the following years and increase it and bring the system to a higher biosecurity level and allow that dramatic disease in the green line that we saw before in incidents. So what kind of means do we need to give to farmers for them to feel that they are in a safe system and they have also the ability to protect themselves? So,
Gabriela, to add there, you're talking about Ph.D, right?
yes, yeah.
That doesn't affect trade, but if you talk about African swine fever, that's going to have an implication on trade, then the whole industry might get affected in a negative way, right?
Right, yeah.
It depends on what disease you're looking at.
Yes, yeah. We don't have data, I think, even for other countries. It's not in the US, but I wonder, I don't think there are data still from the African swine fever to see what are the consequences for producers. Hopefully it won't come to the US, and so maybe we don't need those data, but yeah.
There's been a fair amount of work in FMD.
And then you can just use the...
Yes.
There's been a fair amount of work in FMD, and there the larger economic effects are due to the trade loss, not the disease. So I would expect confined to swine, but the same thing for African swine fever.
Okay. Yeah. All right. I'm going backward. That's why. Okay. So these are really great reflections. I hope we can continue the discussion. Let's go to the last stage of the presentation so we can go into the discussion. So we want to give you an idea. So if we have really good fundings, there are some dreams we want for us to come true. What we want to implement in our model are farm conglomerates, so business with contractor, out-of-state shipments, and then develop also some interactive models so we can test decisions made by players. And then one really great thing is to make our agent bring them from just being reactive to information to become intelligent. And what it means to be intelligent is, Ollin will tell you all about intelligence.
Thank you, Gabriela. Well, we first need to know what do we need by intelligence in this area or scenarios. Like from my previous presentation, you remember that people are reactive to the things that they have presented in the past. So we need this type of diagrams to understand what's happening there. So we have an agent who takes an action, and that action makes a repercussion on the environment. And that environment will be seen by the interpreter, who could also be the same agent. And if we have a reward in that state, we will continue to make the same decisions. But if we have like an inverse reward, if we lost money, then we will have a different kind of action. So what drives us to make an action is to protect our investment. So in this scenario, we're trying to understand how an agent can optimize their earnings, and not only for that certain agent, but we can also see it for the whole system. So if we make intelligent agents, we can optimize the decisions for each specific agent and for policymakers. So that's very important. As we've seen in the past, there are the people in the real world have different behaviors through the system. And this is like the same things that I presented in the morning, so I will skip that. But we can also see that there are certain information treatments that represents a more impactful way of learning to the agents. So if we understand how to make the agents intelligent to the system to make them optimize their earnings, we can also optimize the system to tell them how they should be doing things. So that means like that there was a really important part in this presentation, that it is a self-looping feed in this system, because what the agent does to the system has a repercussion on the system, and the system will have the same repercussion on the agent. So we need to understand how to make intelligent agents in order to optimize the whole thing. So why learning matters? So to understand learning, it makes us improve engagement in policies, and we can have targeted efforts. I'm not meaning that we shouldn't be trying to make everybody understand the importance of investing in biosecurity, but if we understand who are the more susceptible persons to invest or to stop investing, that could lead us to spend less money on policies, and that means optimal allocation of resources. And that's it for me.
You want to go something?
No, you go for
No,
it.
you go.
You go for it.
Okay. All right. Let's summarize so we can go to the discussion. So what we learned is that high specialized networks are more vulnerable to disease. Slaughter plants, feed mills can potentially become super spreaders. And then that high risk tolerance increases the variability or unpredictability of disease incidence and market dynamics in the system. So this is our summary. I want to remind you about our adaptive approach. So we learn from the games, we implement what we learn into the ABM. The ABM gives us new ideas, okay, on human behaviors, and then we feed them back into new games. We learn more, and we want basically to go as close as possible to the reality, and design better plans, better policies to make the system really resilient to disease. Okay, Chris, you're ready? Okay.
I have one. My name is John Blue with Truffle Media Networks. Can you address some of this in terms of independent verification and validation on the models? Can you talk about some of the other efforts to expand on that so that the trust on the producer side is higher, so when they see this, they believe it?
Yes, so part of the verification or the validation comes from having real data. For example, when we talk about behavior, we can validate this because we have the games to back up, right? So those games, I don't know what's going on. Oh, thank you. Those games that have that provide us real data somehow they do strengthen the behavioral side of the model. Then when we calibrate the model, so we have this data, the records from disease incidents collected to back up also the output in our model. And then, well, the part of the market is it's new, so we still don't have the data to verify whether the model really reflect reality, but the fact that we were able to reproduce those high prices in the beginning when there was the high disease impact in 2014, well, that's a good indication that the market model has some good features in it, believable.
You want to mention the data for who we worked with to get the data for this production units and all that sort of stuff?
Right, also, yeah, that's right. Oh my God, yes. So the farms, so when you saw the ABM in the beginning, so we have, these are data that reflect a survey from USDA, where so these farms are placed. This is Duplin County, okay, and we don't have we can't access the real positions because it's private information. But the data we were accessing that we had available maintain the density of the real system. So. Also, we have the exact number of producers, the type of farms, so whether they're win to finish, whether they're farrow to win. So this is also realistic, and their capacity is also it's real numbers. Okay, so the only thing is really the actual positions. The rest is surveys.
And if I like to just one other addition. Yeah, one other addition, and that is Steve and others have helped us to get some access to actual production chains. And so part of this is also building rapport with those production chains to get their actual movement data and their actual geolocated locations of their facilities and their biosecurity adoptions. And so, and then some of these production chains that Steve particularly works with, they have very high-level data on disease spread. So now that we have the basic mechanisms in place, it might be another time to go back and just to reiterate that we could be eventually developing tools for production chains that realistically simulate disease spread, different kind of characteristics of disease spread in a very much realized, where these facilities are actually exactly where they are, and the truck routes and everything else are pretty close to how it really works.
Yeah, in particular, this makes me think of the networks. So the data that Steve helped us use, or getting access to, helped us in coding the frequency of movement, which is essential, especially for PEDV. And what we're going to improve on is the structure of the network, which is like more complex than what we're using now. We'll get to that, but it's all real data and from real producers.
Steve Dreitz. Just to follow up on Mike's comments about the Ph.D. versus ASF, trade implication disease, I think at the time of Ph.D., it was kind of the last man standing. We're going to try to prevent this out of our production system, and those that were successful reaped the huge economic benefits of that. It's kind of changed with ASF in that this is a trade implication disease, and even if my neighbor gets it, it's going to be a huge implication for me. And that's been one of the motivators amongst the swine veterinary community and the swine industry to cooperate with each other. So there's this human component of it that's a little different than this disease now because of the trade implications. So we're seeing a little different behavior. So I'd be interested to see you guys adapt your model to that kind of trade scenario type disease as well.
Salah Isa with USDA NIFA. I'm very interested with that question about intelligent agent because there is also a negative feedback loop if everybody else is doing biosecurity, especially for the people who are slightly risk tolerant. It's like, hey, I could save up some money and get higher return by not adopting biosecurity. So like,
is that like the freeloader effect?
In a sense, yeah.
Yes, that's a very important thing to think about. Also, if we add memory to the agents, that they will remember, oh, I was investing and then I got a disease. Like, why should I still be investing if I'm still getting the disease? But if you're like trying to optimize your earnings, like that should be a transient. Do you know the word I'm trying to use? Like, I don't know. It will pass, and in the long run, you will have agents that are trying to adopt, and in which scenarios are the best ones. And also for the thing that I said, that optimizing for an agent level and also a policymaker level, we can have two strategies to make them like engaged in the investment. So that could be really important, and the results that we get from there can be also like used to understand what are driving people to stop investing, and that can makes us understand how to engage them into invest.
Right. If I may. Yeah, I think that's a really, really good point. This free rider effect is something we've been nervous about. So this can also be a potential for future simulations to try to understand if we test the effects of maybe some indemnity practices, how that may affect this risk tolerant group. Perhaps they'll respond more to carrots, perhaps it sticks. But these are all in our feedback loop, our experimental process. I think we can start thinking about these and trying to retailer our design to incorporate these problems moving forward.
Helen Aceto, University of Pennsylvania. We did some work in the past looking at vaccination strategies, actually, if you do have a disease outbreak. And I was interested to see that even with 25% uptake, you still get a pretty big depression in spreads of disease. So it sort of has some aspects almost of herd immunity about it. So, we identified dangerousness of farms, which were aspects like size and that type of thing. So have you ever tried to look at specifically targeted, try to get uptake specifically targeting the most dangerous farms that could be implicated in disease spread should you have an outbreak, to get them to adopt biosecurity quicker than others? And are they more likely to do it, if you have any idea about that one?
Right, and I think we can tailor some of this agent-based model into a decision support tool in that effect. So using these Monte Carlo simulations, right, we can try to really identify these super spreader nodes, and then perhaps there could be some more government intervention or some sort of indemnities tailored to these high-risk facilities that could potentially really cause a significant outbreak. That's a good point.
So the idea is if we are tailoring products that are specific to specific production chains, the diagnostics would be to be able to identify where the most vulnerable or the outbound node, those that are most likely to be susceptible to disease spread and those that are most likely to spread the disease, and to target that. So there's that from the insider understanding, and then they can, through their contracts and whatnot, ensure compliance at certain levels. And then from the governmental level, I think the idea of indemnification and some of the things that Glenn talked about this morning, that some incentives around indemnification, I think that's a clear signal you're getting from us across the board. And whether it's a blanket or whether it's targeted, when we get these tools refined and calibrated and validated, that's a precision regulation that we might be able to begin to move towards, so that we're being efficient with our regulatory powers.
I'm going to add just one thing. So the first results that we saw from Serge Wiltshire, in his analysis of the network structure, he found that, for example, feed mills and slaughter plants were really the weak points and potentially super spreaders. So that's probably like a first step to what you're mentioning. Mm-hmm.
That's what to go to John's point, the modeling, that's where I think this model really represents reality closer, is because that's been the emerging thing in the swine industry, is that packing plants and feed mills are nodes of transmission that hadn't been well described before, and you're picking that up in your model now.
Yeah, it did. Mm-hmm. Because they're really highly connected. So they really are hub for the system, for the network.
Chris Heine. So I have a question with the trade implications with FMD versus PDV, which is more a personal part. With the gamification model, the person was making money solely off of their decisions, and it would go into their bank account. Does that change any from sort of the social science perspective if their decision making affects someone else? Because I know I've seen that when you play games with people, that how I bet affects somebody sitting next to me, that changes my behavior versus if it's only me benefiting.
Yeah, that's a really good point. And we're actually in the development right now of building these actual multiplayer versions of these games, so we can see what is that social effect, if there's cooperation or more strategy involved. How will that affect their decision-making process if they know that someone they can see, their direct neighbor, might be potentially harmed by their decisions they're making. So yeah, we're interested in looking into that social process as well.
Corey Meyer from Griffin Scientific. I was wondering if you've considered incorporating sort of disease reporting elements into the model, since that plays into speed of detection and situational awareness, which we saw can influence whether someone implements biosecurity or even higher level interventions, sort of above the farm level.
That's a really good question. Want to discuss the bets?
Yeah, unfortunately, it was a little bit too fast for me to catch.
Oh, I'm sorry.
Would you be able to just
reporting, whether we would include disease reporting prevalence in the system?
So it's, yes, I have it coded, and I plan to run some scenarios on that. So one agent that we added, which is the veterinarian, has the role to deliver information to the agents, to producers in particular. And what it's coded there is the willingness to report after receiving the information, or just simply once they get infected, there is that we can include a probability of that agent to report to the veterinarian or to another agent that could be the government. Yeah, it can be done, and part of it's already coded. Yep.
So Lucas Pantaleon. So very interesting, and around thinking around behavior, I think this model that you're showing here is very cool. And have you tried these as an educational tool at all the different levels of your pyramid?
Brilliant.
And if you have, or if you're thinking about it, you think this tool will change behavior, will help you to change behavior?
Yes, we are right in the process of doing that. We are interacting with the education team. Potentially, yes, because there is a potential for changing behavior, because underneath, right, we are including the data from the games, and we see that there is already a change in behavior even when we think about the tactical level and the operational level. And something that Jeanette was mentioning yesterday when we were talking about developing this educational tool is the importance for producers or owners or managers to see the consequences of their decision at the farm level, to make them especially aware that that decision can percolate through the system. And so if they don't have good biosecurity, the rest of the system can be affected. So I think there is really a good potential for education. I don't know how many, if it's common in the production system to have an awareness of the rest of the system, whether people have a good feeling of this effect, this rippling effect of their actions. Is anybody knows? Is it something people are really aware? Or is it something that can be helpful? Yeah, I don't know.
Yeah, Asim Zia from University of Vermont. I just wanted to comment on the intelligent question that you asked about the intelligent agents, and just elaborate a little bit on that. I think that there is a lot of potential to advance the existing USD AFS model that's just based on Markov chain network dynamics, and add these kind of agent-based models to those. And some of these reinforcement learning approaches that we've started to experiment with, but also some of these social learning approaches like the network effects and these free rider effects could be tested in this kind of environment. But for us to do that, we need to have access to realistic data sets that are embedded in those existing national models. I mean, of course, as part of this grant, our focus was on demonstrating that we can build a model like this. But definitely, we are interested in hearing your perspective and your response that if we pitch in another proposal for the next 5 years, looking at making these models, integrating them with those network-based existing models, would that be something that might be of interest to USD and IFA? And also, making available some of these data sets that we don't have necessarily access to simulate these national level dynamics. Thank you.
We have time maybe for one more question. If there's any more comments,
I think, thanks. Michelle Colby, USD and IFA. I think making data available is really an important concept, and that's something that is actually built into the majority of our grants in terms of making data available through the data libraries. If there is data that you all need access to, that's something that we can certainly facilitate to the extent that we have knowledge of its existence and can help facilitate those conversations. That's something that I did a lot of in my past life at the Department of Homeland Security. And I think as we move the conversations forward tomorrow, looking at how that can be done in a constructive basis with the projects that move forward out of this is going to be really, really important.
So I think that wraps up this part of the SEGS session. Thank you for your comments and